Hello, hello, hello. This is Nicholas on this lovely Monday afternoon, wanting to talk to you today about the second derivative test for 3D real valued functions. I find that this is a topic in Calculus 3 textbooks that is very much done poorly and isn't addressed to the fullest extent in terms of the theory behind it. So I want to start first with an analogy to the single variable second derivative test to motivate me talking about that for a 2D, in other words, with two inputs, that type of function, z equals f of x, y. So in single variable, a quadratic approximation to a transcendental function, which I'll call t sub 2 of x because that's the second order approximation, is at the point A. Well, if it's any good, obviously we have to equal the functional value at A. And then we add on a f prime of A times x minus A. And together, this right here is the linearization, the linear approximation of f at the point A. And then we add on a plus 1/2 f double prime of A times x minus A squared. And then all this taken together is a quadratic approximation of f at the point A. Now, if we are finding ourselves at a critical point, in other words, where the derivative equals 0 of this transcendental function t sub 2 of x, then that means that this is equal to 0 and this whole term goes away. And so really what matters for determining whether this function exhibits a local maximum or a local minimum at its critical point is the sign of f double prime, right? Because we really have some number plus 1/2 times all this. And the only thing that's going to change right at the point, this isn't going to change, we could ignore it. This is just a constant, so it's just shifting up or down. So really, and then we have a 1/2, so we can kind of ignore that. And so really what matters is this f double prime of A, the sign of it, right? So, and we were taught, if f double prime of A is positive, right, that's like positive concavity, that's going like this, it's a local minimum. Negative concavity like that, it's a local maximum. Now, I want to extend this idea of a quadratic approximation to a multivariable function. And as it turns out, the quadratic approximation for an ND multivariable function is t sub 2 of the vector x. So the vector x would have like components. This actually represents n inputs, right? Because the vector x is x sub 1, x sub 2, dot, 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 x sub n. Okay. So t sub 2 of now the vector x equals, right? Still have to equal the functional value at that same vector input, plus now the gradient of f of A times the vector x minus the vector A, plus 1/2 times the vector x minus the vector A, dotted with what's known as the Hessian matrix evaluated at the vector A times the vector x minus the vector A. Now, this might look really scary, and honestly, at first, I thought it did too. And I'm going to walk through this through each step. Now, the second derivative test that we're concerned with in like a typical Calc 3 class is limited to just functions f that are real valued with two independent variables and one dependent variable. So that'd be functions of the form z equals f of x, y. So we're going to transform this now into what we're talking about more specifically, which is t sub 2 of the vector x. And actually, I'll just write it now as t sub 2 of x comma y equals f of, I'll call it x naught comma y naught at the specific point, plus now the gradient of f for a 2D, two input type function would be just the partials of all of its independent variables. So partial of f with respect to x, partial of y with respect to, partial of f with respect to x, partial of f with respect to y. And then now the vector x minus the vector A would be x minus x naught, y minus y naught. Okay, now this is where it gets a little more cumbersome to write, so I need to move this over just a tad. Okay, to give myself the most room. Now, plus 1/2 times x minus x naught, y minus y naught, dotted with, and now maybe I'll take a side note here to define this Hessian matrix. So the Hessian matrix is just a generalized matrix, a special type of matrix where each entry is formed by all possible second partials of the function. So the Hessian matrix for a function of the form z equals f of xy is really not that bad. If it's evaluated at the vector a, say, it'd be the second partial of f with respect to x, the partial of f, say, with respect to x and then y, the partial of f with respect to y and then x, or the second partial of f with respect to y, right? So which ways can you take the second ordered partials of f? You can do it with respect to x twice, with respect to x and then y, with respect to y and then x, or with respect to y twice. And now one important thing to note, though, is that this matrix will always be symmetric about that line, that red line that I've drawn right there. In other words, in this particular case, these two values will be equal, right? It doesn't matter the order in which you take the partials. F sub xy equals f sub yx by Clairaut's theorem for a continuous function, at least. And that's what we're going to be dealing with here. So that reduces the computation of this Hessian matrix really to just to 3 entries, this, and this. Okay, so that matrix now is, again, second partial of f with respect to x, partial of f with respect to x and then y, partial of f with respect to y and then x, or second partial of f with respect to y. And then I'm still going to have to multiply that by x minus x naught, y minus y naught. Okay. Now, when you do all of this multiplication, and I do want to clarify the notation here, what this means is that we're first doing matrix vector multiplication, this matrix by this vector. We're going to get another matrix, aka another vector, and then we're going to dot that vector with this vector, and then multiply all that by 1/2. That's what this notation means. When you do multiply all of this out, what you're going to get is, it might look scary at first, but it's actually kind of nice. So you're going to get, here we go, you're going to get f of x naught comma y naught, when you're evaluating this at the point x naught comma y naught, of course, plus the partial of f with respect to x, and that partial is going to be evaluated at x naught comma y naught, but I'm not going to write like x naught comma y naught forever, because it's going to take like 3 lines to write. Just implicitly know that that's what I'm talking about. So partial of f with respect to x, evaluated at x naught comma y naught, times x minus x naught, plus partial of f with respect to y, times y minus y naught, plus, and I'm going to write it like this, 1 over 2 factorial times the second partial of f with respect to x times x minus x naught squared, plus 2 times the partial of f with respect to x and then y of x minus x naught, dang, I thought I could write it all in one line, y minus y naught, plus second partial of f with respect to y times y minus y naught squared. So this here is all being multiplied by this 1 over 2 factorial. Okay, now let's talk about this. So all I did to get this, well, not all, but I mean, did matrix vector multiplication, dot product of this vector with the vector that results from this multiplication, dot product here, right, I should have wrote it more explicitly. The gradient of f dotted with x minus a. So I dotted these and then added that. So there is a strong analogy between the multivariable Taylor polynomial for f of x, y, and the single variable Taylor polynomial for just f of x, but it really only works up to the linear term, right? So as it turns out, this here, I'll underline it actually, this here represents a tangent, in this case a tangent plane approximation to the function f of x, y at the point x naught comma y naught. And one way to see this is to remember that the directional derivative for a real valued function d sub v of f of the vector a is the gradient of f of a. Oops, I did the vector twice there. The gradient of f of a dotted with that vector v. And if we're talking about a level set of the function f, then its output isn't changing. F's output isn't changing. And then so certainly its derivative would be 0 if the output is a constant, right? So on a level set, we have that 0 is equal to the gradient of f dotted with the vector v. And what this means is that the gradient of f is perpendicular to the velocity vector v, the tangent vector at that level set. So, and we can always view a function f as a level set of a higher dimensional function, right? If we have z equals f of x, y, we can view this as f of x comma y comma z equals 0, right? Just subtract this f of x, y over to the other side. And so that's really a very powerful result, because what that tells you now is that the gradient vector acts as your normal vector. And right, what is the equation that is defining of a plane? It's the normal vector dotted with the vector x is equal to the normal vector dotted with the vector x naught formed by the components of your specific point. So what is the normal vector? It's just partial of f with respect to x, partial of f with respect to y, dotted with the vector x, which is xy, is equal to the vector n dotted with the vector x naught, partial of f with respect to x, partial of f with respect to y, and we're going to dot that with x naught comma y naught. And so that gives you this right here. And then, of course, if the tangent plane approximation is any good, it also has to match the functional value there. So we add that term. Now, so that's an understanding up to the linear part. Now we want to talk about the quadratic part. And in fact, to talk about the quadratic part, what I'm first going to do is I'm going to put this in parentheses, and I'm going to write it as it being all multiplied by plus 1 over 1 factorial. And this is really being multiplied by 1 over 0 factorial right here. So it does appear that there's a pattern, right, similar to the single variable case, where, right, this next term would be plus a 6th, dot, 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 and then plus a 24th, right? There is that pattern that's going on here as well. Now, as far as how we actually think about this second term, well, we need to first talk about something called quadratic forms. So this is typically where the textbooks just don't mention anything about quadratic forms, which I find it a little sad, but that's why I'm talking about it to you today. So a quadratic form that is analogous to our case of dealing with functions that have 2 input variables and 1 output variable. It's just any equation of the form ax squared plus 2bxy plus c y squared. And notice here that there's this 2 here that matches with this 2 here. And realize that we got this 2 right here because when we did this multiplication up here, we got a partial of f with respect to x and then y times y minus y naught plus a partial of f with respect to y and then x of x minus x naught. But these two partials are identical because the function is assumed to be continuous. And so we get a 2 right here. So we are in fact dealing, this quadratic term here is a quadratic form. Now, the quadratic form in a higher number of dimensions, right, is usually, well, I'll show you, here's how it's represented in this particular two-dimensional case. It's represented as the transpose of a vector x times some matrix M times that same vector x, which we think of as a matrix in general. So that would be x, y by the matrix A, B, B, C times the vector, which is really matrix, x, y. And when you do this, right, you are going to get ax squared plus 2bx plus cy squared. Now, what we're asking here, because realize, right, if we're to determine, if we have a critical point of the function f of x, y, and we're to talk about whether this represents a local maximum or a local minimum, we need to be able to tell when this quadratic term here, when this quadratic term here is positive, negative, or neither, right? So it is analogous to the single variable case, really. So this is what we're going to be exploring, is how to tell whether a quadratic form in 2D is positive, negative, or neither. And so what I'm going to do is I'm going to kind of reduce this to just a single variable case, right? So what I'm going to do is I'm going to let y be equal to y naught. I'm going to get ax squared plus 2by naught x plus cy naught squared. And now realize that y naught is a number here. X is still a variable. This is just the equation of a typical algebra 2 parabola. And so solving for x via the quadratic formula, we get x is equal to negative 2by naught plus or minus the square root of 4b b squared y naught squared minus 4ac y naught squared all over 2a, which simplifies to y naught times negative b plus or minus the square root of b squared minus ac over over a. Okay, now what this tells us then is that if we have b squared minus ac being less than 0, then we have no real roots, and the function is entirely positive or negative. Right, that's what would happen if we have no real roots. And then likewise, if b squared minus ac is negative, that means that ac minus b squared is positive. Okay, and then if b squared minus ac is positive, we do have real roots, and so the function is not entirely positive or negative, which is not really what we want. In this case, that means we'd have like negative concavity in one direction, positive concavity in the other direction, and at this point, we'd have what's known as a saddle point. Actually, I kind of think it's funny to call them Pringle points because most people don't really know what a saddle looks like anymore. But if everyone knows what the shape of a Pringle looks like, if you go in one direction of the Pringle, there's positive concavity. And on the other direction of the Pringle, there's negative concavity. And so it's not actually a local maximum or a local minimum. So in this case here, in the first case, we have an extrema. Oh, and then also, if b squared minus ac is positive, then ac minus b squared is negative. And in the second case, then, we would have a saddle point, no extrema. So why did I go through the trouble here of mentioning ac minus b squared instead of b squared minus ac? Well, because the determinant of the matrix A, B, B, C, which, by the way, was defining of the quadratic form, that determinant is AC minus B squared. And so what that tells you, this is why we want to write it like in this way, because when we're dealing with extrema of higher order functions, it's important to be able to generalize that in terms of the determinant of a matrix. So now, another thing to realize then, going back up to right here, just standard algebra 2 rules now. If if the leading coefficient is positive, we have the parabola going up, and so we have a global minimum. And then if A is negative, the parabola is going down, we have a global maximum. Or, local maximum. It depends on your domain in which you're considering. So now, what are these coefficients A, B, B, C? Well, if you look at this right here, and if you look at this right here, you will see that this is this. This third term, the quadratic term, is a quadratic form, right? You always have a degree 2. You have an x squared, an xy, or a y squared. And so what that tells you is that this matrix A, B, B, C is the matrix. It's the 2x2 Hessian matrix. It's second partial of f with respect to x, partial of f with respect to x and then y, partial of f with respect to y and then x, or second partial of f with respect to y. And so now what we have actually is a total proof of the second derivative test, which I will write out now for you like how a calc text would. So the second derivative test says that at a critical point, if the determinant of H, the Hessian matrix, is greater than 0, right? If this is greater than 0, we have an extrema. So if it's greater than 0, and if A, which is the second partial of f with respect to x, is greater than 0, we have a global, is greater than 0, we have a global min. The determinant of H is less than 0, or I'm sorry, the determinant of H is greater than 0 now. It's greater than 0, and the second partial of f with respect to x is negative, we have a global max. If the determinant of H is negative, right, if AC minus B squared is negative, we have a saddle point, and that's not really something that we look forward to. That looks like an equals. And then if other, in other words, if the determinant of H is equal to 0, or if the second partial of f is equal to 0, the test fails. We have to use other methods to classify the point in question. So this really is a full explanation of the second derivative test that I really would wish a lot of calc textbooks would include. I think it is very instructional. And so, and there was certainly nothing that was beyond the scope of, if you understand Calc 3, there was nothing here that I mentioned that was beyond the scope of a Calculus 3 text. So I think with that now,